Anybody have any homework questions or anything?
Can we do number one on internal loads?
Sure.
Kind of struggling with it. Even with the borders by each of the, as you do each of the parts.
Okay.
Yeah. Went to office hours.
Okay, internal loads. Number 1. 2 meters long. 15 pounds. So you have a pin joint over on this side, a roller at the middle, a downward force of 15,000 here. 30,000 at the midpoint between those two joints. You have a 30,000 force going that way. Okay. And the whole thing is 2 meters long, so this is 1 meter, half a meter, and half a meter. I said last time that pretty soon we're going to start doing this with distributed loads. We haven't done that yet. We've just done point loads. Have you noticed that the example we did and this problem here are like the first two problems we've done in this whole class almost, where we haven't had any masses given for anything? Anybody notice a relationship between those two things? So gravity, I mean, when you're treating something as a rigid body, the weight always acts at the center of mass. But gravity doesn't really calculate your center of mass and then apply a point force there. It applies a little bit of force, a distributed load, everywhere, you know? And so when we start doing internal loads, weight is going to have to be treated as a distributed load. What?
I was thinking this the other day.
Yeah.
This one had nothing to do with this, but like, you know, you talked about like pole vaulting and changing your center of mass.
Yeah.
When you're swinging on a swing, like as a little kid, and you like rock back and forth to get yourself going, is that changing your center of mass?
I have never, I know people have done that calculation. I remember seeing when I was applying to college, somebody like just had written a paper on how that works. Like there had been sort of like a conventional wisdom and someone was like, I don't think that's how it works. I've never read the thing. Yes, somehow it definitely has to do with changing your center of mass. You're right. And I would think, I mean, just there's a paper on it, smart people, whatever. But just my thought on it is that, yeah, like if you're, I think it's the same thing as like people doing giant swings on high bar, you know, where they're just going around in gymnastics. When you're on the way down, you stretch out as far as possible to get your center of mass far away from the bar. That produces a big moment. So you got this big moment pulling you down. And then on the way up, they bring their feet in a little bit to bring their center of mass a little closer to the bar, and so it's easier to get up. And I would guess it seems like it must be something related to that. But yes, I think you're right.
Angular momentum.
Yeah, right. I think you could probably think of it through Newton's laws, or you could think of it. Well, conservation of angular momentum is derived from Newton's laws. So yeah, you could do it in either of those two ways. I'm sure you could. Probably the easiest way to do it would be through conservation of energy, you know. But okay, so after we've talked about how to treat distributed loads in internal loads problems, then we can start adding mass to things. Right now, we can't treat the weight. Okay. So that is to say, this is all the information we need here. The first step always is you have to turn what you know about those joints into external loads. So the first thing we have to do is a statics problem to find those external loads. So we have these forces. And we have an unknown force here. I'll call that RA. And this one's a pin. I'll call that RB. Every time you draw a free body diagram and go to Newton's laws, if you want, you could write out that full table. It's not really necessary with horizontal beams, but feel free. I mean, you got time in tests, you know. But so Newton's second law says 0, negative 15,000 plus 0 RA plus 30,000, 0, plus RBX, RBY is equal to 0. Are we going to be able to solve this? I'm sort of, maybe you should have thought of this. I think we should be able to solve it because because this is just a scalar and this is a vector. So unless something's, one of our equations is a linear multiple of another one, we should be able to do this. 3 variables is the maximum number of variables you can solve for in a 2D rigid body problem. Okay. And then, RBX we can already calculate. So that's negative 30,000. Moment equation. Once I go to the internal loads, I'm always going to do my about point at the left end point. You can always do it for the external loads too, but I'm going to do it here to just try to simplify this calculation since I'm sort of doing it in my head. So the 15,000, so we have plus or minus force of 15,000 times a moment arm of 2. Is that clockwise or counterclockwise?
Yeah.
Counter. So that's positive. Then we have plus or minus RA times the moment arm of 1. Is that clockwise or counterclockwise? Clockwise, so that's negative. Then we have the 30,000. Does that produce a moment? Nope, that's right down along the long axis of the beam. And the RB is at the about point. So this is 0. And so we get that RA is positive 30,000. RA is 30,000. So RBY is negative 15,000. So we get RA is 30,000 newtons. RB is negative 30,000. Positive 15,000. Everyone agree with my head math on that one? Okay. All right, well, we have so there's the two endpoints. And then in addition to those two endpoints, we have these 2 points where those subfunctions of the piecewise function is going to change. Okay, so you can think of like we have n equals 4. How many cuts are we going to need?
3.
3, right. So one with the right end between those two, one with the right end between those two, and one with the right end between those two.
Question. So we have this pin joint on the right side.
Yeah.
And if you do your cut starting from the left,
Mhm.
never actually, the
Right.
pin joint never actually shows
Yep,
up.
that's right.
But it showed up earlier when we were calculating RA.
Yes,
Is that how it works?
that's right. That's right. So
It
now
still matters.
it matters,
Okay.
but now it's done mattering. Now it's baked into our other answers.
Okay.
Yep. Okay, so we have 3 cuts to do. So let's get to work. Cut 1. This is for x values between 0 and 1. And so our free body diagram has a length of x. We have that downward 15,000 Newton force because in every one of these cuts, always, we're starting all the way at the left of the beam. And the x only refers to the right end of the beam. Okay? I mean, not the right end of the beam, the right end of the cut. Okay, so 15,000 there. We haven't gotten to the RA yet. So now the only other external loads are our T, V, and M. So Newton's second law says 0, negative 15,000 plus T, negative V. Save some electronic paper, put those two together. So we get an internal tension of 0, an internal shear force of negative 15,000, and now the moment equation, and my about point is here, like it always is. So the 15,000 doesn't do anything. The T doesn't do anything. We have positive M. Since the length of this thing is x, we have, x times v. That produces a clockwise moment, so this is minus vx equals 0. And so that tells us that m is equal to vx. V is negative 15,000. So m is equal to negative 15,000 x. Any questions about that cut? Okay, so now we go to cut 2. And remember, so cut 2 is going to be for x's between 1 and 1.5. Remember that we're coming up with a piecewise function of x for each one of these internal loads. So we have these functions here, but remember that these are only valid on the interval from 0 to 1, okay? When we're talking about x's outside of that range, we have to use different subfunctions. Any questions about that?
The interval 0 to 1, where could you show us the full free body?
Yeah.
On that?
Yeah. So for x's from just basically slivers of a piece of this thing, just slightly longer than 0, to pieces that are almost 1, 0.9999999. And now we're doing the second cut, and we're going to be doing, this is going to be valid. Okay, so our cut is going to be all the way from the left end to some arbitrary point between these two point loads. But it's only valid for x's. Remember, x refers to the right end. It doesn't refer to the piece. So now we're dealing with x's in that range. Okay, so we go all the way from over here with our piece. So we still have that 15,000 Newton, okay? I mean, notice that's happening outside of the range of valid x values, okay? That's because the x values only refer to the right end. We're putting all this stuff in because we know it and it makes the calculations easier. All we're trying to calculate is internal loads over here, x meters from the left end. Okay, so what do we have now that's new? We have RA, so we have a 30,000 Newton force here. And then we have our internal loads. And so let me write down the distances. So this distance, no matter what x is, that roller is 1 meter from the left end, right? So that doesn't depend on x. So this is just going to be 1. And then where that right end is x meters from the left end. We don't know what that is. And x has to be between 1 and 1.5. Okay, so Newton's second law says 0, negative 15,000 plus 0, positive 30,000 plus t negative v so t still is equal to 0 on this interval. V is equal to positive 15,000. And now the moment equation with the about point at the left. We have a counterclockwise moment of 30,000 times 1. And then we have a couple that we're adding on. And then minus Vx. So m is equal to Vx minus 30,000. We figured out that on this interval, V is 15,000. So m is equal to 15,000 x minus 30,000. And these subfunctions are valid on the interval from 1 to 1.5, excluding the endpoints. We haven't calculated anything at the endpoints, and we're, you remember from last time, we just sort of gloss over that at the end. Any questions about that cut? We have one more to go. So cut 3. is for x's between the 30,000 Newton horizontal force and the external load at the right end. So this is for x's between 1.5 and 2. So we have the 15,000 here. We have the 30,000 here. We have the 30,000 horizontal force there. We haven't, no matter what we choose, what our x is, we haven't made it all the way to the endpoint, so we're not going to have that pin joint force. And so the only thing we have left is T, V, and M. So Newton's second law says 0, negative 15,000, plus 30,000. I'll do the vertical one first. Plus 30,000, 0. Plus T negative V is equal to zeros. So now we do have an internal tension for the first time because of that horizontal force. So T is equal to negative 30,000. On this interval, is this beam in tension or compression? Compression, yep. A negative value of tension means compression. V is equal to positive 15,000. And now the moment equation. We have 30,000 times its moment arm of 1. This horizontal 30,000 it's horizontal. It's acting right along the long axis, so that doesn't produce a moment. So then all we have left are plus the couple minus Vx is equal to 0. So M is equal to Vx minus 30,000. And so M is equal to 15,000 x minus 30,000. And these functions are only valid for the interval 1.5 to 2. Yep.
So each cut picks up one more force.
Yes, each, it picks up, there are 3 things it can pick up. A point force, a point couple, or what we'll see later is a change in the distributed load function.
Okay.
Okay. All right, so you could write all of these as piecewise functions. I don't ask you to do that in homework, but you should think of it that way, you know. So T as a function of x is 0 for x's between 0 and 1.5. So you can see it's 0 from 0 to 1.5. Oh yeah, 0 from 0 to 1, 0 from 1 to 1.5, and then negative 30,000 from 1.5 to 2. The shear force is a function of x. From 0 to 1, it's negative 15,000. From 1 to 1.5, it's positive 15,000. From 1.5 to 2, it's positive 15,000. So this is negative 15,000 for x from 0 to 1, and positive 15,000 for x from 1 to 2. And then the bending moment from 0 to 1, it's negative 15,000x. From 1 to 1.5, it's positive 15,000x minus 30,000. It stays the same from 1.5 to 2. So this is negative 15,000x for x values from 0 to 1. And positive 15,000x minus 30,000 for x's from 1 to 2. Okay? And I don't mean to draw this out unnecessarily, but let's look at what those functions look like. So for the internal tension, there's 1, 1.5, 2. We have 0 for the internal tension, all the way to 1.5. And then from 1.5 to 2, we have a value of negative 30,000. And so we just connect those. That makes no sense mathematically, connecting that like that. But it does kind of make engineering sense, because if you're imagining that, those don't always agree with each. If you imagine that as being a very narrow distributed load, then what you would get based on how dull that contact point is or how fine that contact point is, you'd get a thing that has a little bit of a tilt to it. If it's a very fine point, it's a very steep tilt to it. If it's very spread out, it would be a shallower thing. And so this really does give kind of a visual representation of what's really happening in some way. If you really hate that, you could make it ever so at an angle, you know, so that I can't tell, but you can tell in your own mind, you know. And then the shear force, negative 15,000 and positive 15,000. So it does this for the first half, this for the second half. And then the last one, the bending moment. This is two linear functions. When x is equal to 1, they have a value of negative 15,000. They're linear. They start at 0. And so they go like that. Any questions about that? We can't do much from these internal load calculations by themselves to figure out where we're worried about this thing breaking. Most of that is going to come in mechanics of materials, deform, when you take that. But you can start to see some of the stuff that we're learning from this. So where are the places that you're concerned about this breaking? In this case, two of these internal loads tell kind of different stories, so it kind of depends on what kind of material you have. Does it have a large elastic region? Is it very brittle? Is it very ductile? It stretches a lot. Well, if this material is very prone to breaking in pure tension and compression, then we can see from this that we're most concerned about it in that last quarter of the length. Okay? Shear force doesn't make much difference. There's no real difference between, look at the absolute value of the shear force, except right at the center point where that roller applies. We have an absolute value of 15,000 for that shear force the whole time, so that doesn't tell us too much. The whole thing is basically the same in that way. But the bending moment, you can tell that from either side as you get closer to the center, if this is a material that's especially prone to breaking due to bending, then we'd be concerned as you get closer to the center of this thing. Okay, so there's really nothing more you can say about that. But I mean, one thing you can say is you don't have to worry too much about the thickness of the material or the strength of material on the left half of this thing. Okay, and we're just starting to learn to tell this story, but you can see how that comes about. If you had a place where any of the internal loads that varied at all got biggest at a single point or got biggest as you approached a single point, then you'd say, like, that is where I'm concerned about this thing. And I want to show you, so the example we did last time tells a little bit of a clearer picture, so I want to write that back up and talk about that. But anybody have any more questions about that problem? Okay. So the example from last time, we had a pin joint over on this side. We had a roller at the middle. We had a horizontal force here of 1,000 newtons. At the right end, we had a 2,000 Newton force and a 600 Newton force. And we got internal loads that looked like this. So this is 600 newtons, this is negative 400 newtons. The shear force went from negative 2,000 to positive 2,000. This one only had stuff going on at the midpoints. And then the bending moment looked like that with a minimum value of negative 2,000 Newton meters. Okay, so can we say anything in this case about where we're concerned about this this object breaking? In this case, yes. So the shear force is basically the same everywhere, except right at that center line. We don't really know what's going on exactly at the center line. That would take a more complicated analysis. The tension says we're most concerned about this thing on the right half, right? The bending moment says we're most concerned as we go toward the center line coming from the right. Well, it says as you approach the center line, combine that with the tension force, and you say like, these two things tell a story where I'm most concerned about what's happening going from the right as you get closer and closer to the center. Okay. That's not, it turns out, you know, when we get to deform, you'll be able to do a thing that'll combine these things in certain ways, and you'll actually be able to do a meaningful analysis. But I just want you to notice that that's like where we're headed with these internal loads. We're trying to figure out where are we concerned about this material breaking or deforming, you know, more than we wanted to deform or whatever. Any questions about that? Okay. Let me do an example with a point couple. We haven't seen one like that. So let's say we have a cantilever beam with a force this way of 10,000 newtons. And at the center, we have a clockwise couple of 2,000 Newton meters and an upward force of 3,000 newtons. We want to calculate the internal loads. We need lengths. Let's say this is 0.5 meter and this is 0.5 meter. So first we're going to calculate, well, this is sort of an interesting thing in this one. So I say always start by calculating the external loads, right? And I'm going to do that. Why not? But I want you to notice something interesting about problems where the only unknown loads happen as a cantilever on the right side, When we go to our cuts, you know, we're going to do one cut that's like from the left end to here, or somewhere in here. Our second cut is going to go from the left end to somewhere in here, and we're never going to see those external loads, okay? So, you can go through this problem and calculate the internal loads without ever figuring out the external loads on the right end. It only happens that way when you have cantilever beams connected on the right side. So sometimes I'll do that on exams because like you can save a little time if you see it, you know. It's not a big deal. I still just always go through and calculate the external loads first. One important reason for that is we'll see that we're going to come up with some sort of sanity checks on this stuff, and you can't sanity check it without having the external loads. So anyways, just something to notice there. I'm gonna still do it the way I always do it. Okay, so we have a force here of 10,000. we have a couple of 2,000 and an upward force of 3,000. And then it's a fixed joint at the right, so I'll call that the force R and the couple MR. And I'll just, for the free body diagram of the whole thing, I'm going to use the about point over at the right. So Newton's second law says negative 10,000, 0, plus 0, positive 3,000, plus Rx, Ry is equal to zeros. Cantilever beams are nice for calculating external loads because everything's uncoupled. So you can just calculate the force first from the force equations and then calculate the couple second from the moment equation. So we get that R is equal to positive 10,000, negative 3,000. And then the moment equation, the 10,000 doesn't produce one. The 2,000 is clockwise. So that's negative 2,000. The 3,000, that also is a clockwise moment. And it's equal to a moment arm of 0.5 times a force of 3,000. And then the only other moment is the couple MR. And so MR is equal to 3,500. Any questions about the external loads? Okay, how many cuts are we going to need for this? 2, yep. And maybe it's sort of obscured by the fact that I have this 3,000 acting at that same point. But even if that wasn't there, we'd have 2. This couple isn't a force, but you still have to treat it as a point where those subfunctions change. Okay. Okay, so our first cut is for x values from 0 to 0.5. And our piece goes all the way from the left end to this x value, somewhere between 0 and 0.5. So we have a 10,000 Newton force there. We haven't gotten to those other external loads yet, so now we just have these. So negative 10,000, 0, plus T negative V is equal to zeros. So T is 10,000. And V is 0. Is this in tension or compression? Tension, yep, because it's positive. Moment equation with the about point at the left, we just have m minus vx is equal to 0. V is 0, so m is also equal to 0 on this interval. So this is for x values from 0 to 0.5. And then cut 2 for x's between 0.5 and 1. So we have the 10,000 We have the upward force of 3,000 now. And the clockwise couple of 2,000. And then T, V, and M. So Newton's second law says negative 10,000, 0, plus 0, positive 3,000, plus T negative V, is equal to zeros. So T is equal to 10,000 again, it's still in tension. V is equal to positive 3,000. The moment equation. What's the moment arm for that 3,000 Newton force?
0.5.
0.5, that's right. And that's a counterclockwise moment, so we have positive 0.5 times 3,000. That 2,000 is clockwise, so we just add it on as a negative 2,000. Then we have plus m minus Vx is equal to 0. So m is equal to Vx plus 500. And so m is equal to 3,000x plus 500. Okay, I don't want you to put this in your notes yet, but I want you to notice something trippy. What's dm dx here? Just take the derivative of that function. What?
It's just the shear force.
It's equal to the shear force, yeah. 3,000. What's dm dx here? Shear force? dm dx. Here we have it in two different places. Shear force, shear force. Okay. So we're going to have some of these derivative relationships coming up. I don't want to like get it as a list in your notes until we talk about distributed loads, but this is how we're going to end up sanity checking this stuff at the end. Okay, any questions? That's all.
Exam Monday.
Oh,
I just
yes. No, the exam for statics is Friday, a week from Friday.
Okay.
But the exam for thermo is Monday.
Okay.
That's right. Yes.
Are we at liberty to move the about point?
You're at liberty to, but don't do it.
Okay.
Yep. I mean, maybe do it once and then you'll see why, like, I'm not going to do that again. But it'll give you the same answers. It's just things get more complicated.
I was just thinking like.
You totally can, yes.
Where more forces happen.
Right. You totally can. You'll just see that.
Don't do it.
Yeah, that's what you'll see. But I totally encourage doing it and seeing why. Yeah.